So this is Big 10. So in this we will solve the question and as well as we summarize some key points from the previous lecture or some extra elaborate of the topic whatever has been taught in the last week. So first mostly sir talked about correlation, second order correlation, which is G2. So correlation and coherence, that is temporal coherence or spatial coherence etc, and also some other topics, but we start with coherence. So what is coherence? So in physics, the coherence expresses the potential for two waves to interfere. Okay, so if two monochromatic beams from single source which always interfere, we know. So physical source are not strictly monochromatic. Okay, so they may be partially coherent, or beams from different source are mutually incoherent. Okay, so coherence is the main phenomena uh, uh, in the interference. So two waves with constant relative phase will be coherent. So the amount of coherence can readily be measured by the interference visibility. Okay, so which looks at the size of interference fringes radiated to the input waves as the phase offset is varied. Okay, so a precise mathematical definition of the degree of coherence is given by means of correlation function, like G2 or G1. G1 is called first order coherence, and while G2 is called second order coherence. Okay, so this coherence describes the statistical similarity of the field, like electromagnetic field or quantum wave packets at 2 points in the space of limit. So if we go to the qualitative concept, like you all had about Young's double slit experiment. So in Young's double slit experiment, this wave plates and this is the screen. So let's say this is the point and light goes to at some point P from here and here. Okay, so let's say this is angle of theta. Okay, so coherence contains several distinct concepts, that is spatial coherence is also happens, and second one is temporal coherence. Okay, so spatial coherence describes the correlation or predictable relation between waves at different points in space, either lateral or longitudinal. Okay, and while the temporal coherence is describes the correlation between waves observed at a different moments in time. Okay, like if we have some time t and t plus tau, so if the phase constant is same, change is same in these two time, then it is called temporal coherence. While if the wave has at x or x plus delta x, and at both places the phase is constant, then it called spatial coherence. Okay, so both type of coherence are observed in the Michelson-Morley experiment and Young's interference experiment. So once fringes are obtained in Michelson interferometer, when one of the mirror is moved away gradually from the beam splitter, so the time for the beam to the travel increases and the fringes becomes dull and finally disappear, so showing temporal coherence. Okay, similarly in double slit experience, if the space between the two slits is increased, the coherence dies gradually and finally the fringes disappear, shows the spatial coherence. Okay, so these two type of coherence can be seen in the different interferometer. Okay, so now uh, if we go to the relationship between the coherence time and the bandwidth, Then if we have tau c coherence time and spectral width delta f, then it should be greater than or equal to 1. Okay, so this is the relationship between coherence time and the bandwidth of the source, you can say. So the some other examples of the temporal coherence. So the wave containing only a single frequency is perfectly correlated with with itself at all time delays. Okay, so in accordance with the above relation, uh, so how can we measure the temporal coherence? So like Michelson interferometer, Mason interferometer, all these interferometer we can calculate the temporal coherence. Similarly, the spatial coherence also. Uh, okay, so this is the some basic key concept for uh, the coherence. Next, come to the what is the G2, which are always talked in this week, some with some lecture. So what is this G2? So this G2 is called second order correlation function. Okay, so second order correlation function, that's why it is called 2 is denoted for the second order correlation at time tau. So is it is the intensity analogous, so it is the function of intensity, while the first order, if you see, so this is the function of amplitude. Okay, and this is the function of intensity, it denotes the intensity, while G1 is the correlation between the amplitude of the electromagnetic waves. Okay, so the way in which the electric field fluctuates in the time, whereas G2 tau quantifies the intensity fluctuation. So in classical optics, if we go, then this G2 tau is often called degree of second order coherence. Okay, so note that here and in following we are referring to the degree of second order temporal coherence. Okay, so which is the one usually considered in generalize of this notation to include the spatial correlations can be found. Okay, so how is it defined? So this second order Z2 correlation tau, if we have beam intensity with I at time t, this is the intensity at time t, then this G2 can be defined like G2 tau is equal to average of I at time t and intensity at time t plus tau upon intensity at time t square. Okay, so where the this bracket is denotes the time average. Okay, time average of the quantity which is written inside the cavity in this bracket. Okay, so from an experimental point of view, if we see this point of view, the number of counts, that is n at time t, registered on a photon counting detector is proportional to the intensity of the impinging beam. Okay, So we can write this classical definition of G2 tau as n t and n at t plus tau divided by time average of nt. Okay, so what is the physical meaning of this one? So we can think this G2 tau as a answering the following question, like I have detected a photon at a time t. What is the probability of detecting another photon at time t plus tau? Like if we are detecting some photon at time t, then what is the probability that we also get the photon at t plus tau time? Okay, so more precisely, if you see, this G2T gives us the degree of correlation between the number of photons detected at time t and at time t plus tau. So this tells us how much the information about the number of photons at time t translates into knowledge of what I will measure at time t plus tau. Okay, so the important note here is a very important value is G2 at tau is equal to 0. Okay, so however, in the way we defining G2, this is also kind of ill definition. If I have measured n photons at time t, what does it means to ask how many photons will be measured at time t plus 0 or at time t? So I will interrupt it in the following, as the number of photon counts at an infinitesimal small time after t. Okay, so what should be the value of G2? Generally we will see. So if the light is bunched, okay, then this G2 0, this will be greater than 1. So this denotes the classical phenomena of light or classical optics. Okay, phenomena. Second one is coherent light. Okay, so for coherent light, if you see, then this G2 0, this will give you this G2 value is 1. Okay, similarly for anti-bunching, or we will see single photon emitter, this is anti-bunched light, so this G2 0, this will be less than 1. Okay, so like for example, this is the time axis. Okay, then this is the tau c, that is coherent, temporal coherent light. Okay, then let's see three type of phenomena. So these two photons, and we will see these three photons is here, and if we see, one photon is at here, and one photon is here, and one photon is here. Similarly in this line, and similarly in this line. Okay, so this photon detector as a function of time anti-bunched, this will be anti-bunch, and this will be randomly, and this will be bunched light. Okay, so what is the difference? The difference is, for bunched light, this phenomena can be happens, this G2 will be greater than 1. Okay, so this for coherent light, like the produced by a laser, the number of photon counts is proportional to the intensity. Okay, so which is why definition in a simple scenario considered here, the constant over time. Okay, So this means that the number of counts at time t and t plus tau are uncorrelated. Hence this g2 tau will be 1 for any tau value. So note that the average number of counts are not uncorrelated in general, and indeed in the simple example of the beam with constant intensity that we are considering here, the averages are constant. Okay, so still the function of the intensity are uncorrelated. So this means that no matter how well I know the distribution of intensity at time t, one will never be able to reduce any uncertainty about the intensity fluctuation at time t plus d tau. Okay, so now this g20 tells us how often we detect two photon at time very close to each other. Okay, so we imagine here to always detect one or zero photon at a time. So while for coherent light the two detector events are uncorrelated, for light produced by other kinds of classical source like chaotic light, or we can have intensity fluctuation on the source, and therefore a tendency of detection events to be sometimes closer to each other. So in these cases one talks of bunched light. Okay, so this means that given a detection event at t, there is a higher probability of another detection event at time t close to t. So this kind of source therefore satisfies g20 is greater than 1. Indeed, it can be shown that classical light source must always satisfy this condition. Okay, so this is mostly classical light condition. So this means that in the classical view of light, this g20 is always less than 1, that is anti-bunched light is not possible. Okay, so why it is important we are talking so much about this g2? So from this last statement we can now see that importance of the this parameter. It allows us to experimentally rule out the classical view of light. Okay, so if we manage experimentally detect anti-bunched light, then we must surrender and admit the necessity of the quantum picture. Okay, so which of course is what actually happened about the experimental detection of anti-bunched light. We sir talked about this Hanbury, Brown and Twist experiment. Okay, so in this experiment one uh, uh, beam splitter is here, one detector is this way and one detector is in here. So this the probability of getting, if the single photon is coming at a time, then it can go either here or either here. So probability at 1 is 0 and probability is half that it come to the one detector. But if it detected by one detector, another detector should be 0. Okay, so this is the important of g2 is we can define and about the classical light and the quantum light nature of the source by using the value of g2. Okay, so that is the some key aspects of this g2 which sir discussed. So now comes to the question. uh, Question number 1 is uh, temporal coherence manifest itself as. So options are: A is a degree of monochromicity of the light, okay, and B is angular speed of light beam. Similarly, this C is the fluctuation in the photon number due to the discrete nature of photons. Similarly, the D option is the spectral width of light. Okay, the option E is the photon energy of the light beam. So temporal coherence, as I talked earlier, the degree of monochromicity of the light is somewhat related to the temporal coherence. Another is spectral width of light. As I say, this tau c and delta f is should be less than 1. Okay, with this relation, sorry, this greater than 1. Okay, so from which you can write these two are the correct answer. Okay, similarly we have question number 2. So question number 2 is the visibility of fringes in Young's double slit experiment is manifested of light. So your options are statistical nature, option B are quantum nature, option C are spatial coherence, and option D is temporal coherence. So as I see earlier, this Young's double slit experiment, whatever this part difference is given by this distance d between two slit, so it means this manifest as a spatial coherence. Okay, so spatial coherence is the correct answer. So statistical nature, I don't think this visibility of fringes can be explained on the wave nature, right? So it does not manifest as a quantum nature of light, as well as temporal coherence also is not valid, and this statistical nature is also not valid for this. No need of this statistical nature to define the Young's double slit experiment. Okay, so we can eliminate these three option, and the correct answer we can choose statistical coherence. Okay. So next in question 3. Question 3 is the delay over which the correlation in phase or amplitude of a wave decreased by a significant amount is defined as. So your options are A, coherence time, tau c, B is coherence length, which is LC, C is pulse width, and D is wavelength of the light, and E is coherence area. Okay, so what will be your answer? The question is the delay over which the correlation in phase or amplitude of the wave decreased by a significant amount. Okay, so this delay is related to time. Okay, so this is coherence time, so this will be the right answer, coherence time. Okay, so next question, question 4. Question 4 is given that consider the following source which is Si with corresponding coherence time tau ci. Okay, so choose the correct answer. The source 1 is given LED, which is delta lambda is somewhat 50 nanometer. Okay, source 2 is given tungsten filament, and spectral width is around 600 nanometer. As 3 is given sun, which this delta lambda is around 1 mm, and as 4, source 4 is given laser, that is delta lambda is 5 nanometer. Okay, so what will be the answer? we have to arrange. Okay, first I give to the so option 1 is tau c1 is less than tau c2 is less than tau c3 is less than tau c4. The v is tau c4 is less than tau c1 is less than tau c2 is less than tau c3. Okay, third is tau c3 is less than tau c2 is less than tau c1 is less than tau c4. And option D is tau c1 is equal to tau c2 is equal to tau c3 equal to tau c4. And E is tau c4 is less than tau c3 is less than tau c2 is less than tau c1. So as I earlier told you, this tau c delta f should be greater than 1. So this tau c is somewhat is greater than 1 by delta f. Okay, so this delta f is given by this. So whatever delta f is less, tau c will be higher. So for the laser will be the highest tau c. So this tau c4 is highest in these two. So all these answers are incorrect. Other than and 5, then is less than this is 50 nanometer. So this S1 will be second highest. So this is only in this one. So this will be the correct answer. Okay. So this question number 4. Sorry, question number 5. Question number 5 is given. The correct mathematical expression for second order correlation function G2 tau is options are A, G2 tau is equal to ET plus tau divided by IT plus tau. The V option is G2 tau is equal to ET plus tau divided by ET plus tau. The C option is G2 tau equal to IT plus tau divided by it plus tau. Option D is G2 tau is equal to ET IT plus tau divided by IT plus tau. And the fifth G2 tau is equal to IT and IT plus tau divided by IT plus tau. So which one will be the correct answer is the question. Okay, so this is E amplitude, but G2 tau is the intensity fluctuation, measure of intensity fluctuation. So this will wrong. G2 tau always E, so this will also wrong. And here if you see, this is given equal to 1, right? So this is also not expression for G2t. So and here is also E is coming amplitude, so this is also right. So this will be your correct answer. Okay, so always this G2 is the IT plus tau and divided by IT and IT plus tau. Okay, so next question number 6. Light is said to be bunched if this G2 tau is less than G2 0, G2 tau is greater than G2 0, G2 tau equal to G2 0, and D is G2 tau equal to 1, and E is G2 tau equal to 0. So the correct answer will be this one, as I discussed earlier also. So question number 7 is this light is said to be anti-bunched if option A is G2 tau is less than G2 0, V is G2 tau is greater than G2 0, C G2 tau is equal to G2 0, and D is G2 tau equal to 1, and E is G2 tau equal to 0. So the correct answer is this one. Okay, for anti-burst we study that G20 is less than 1. Okay, question number 8 next. The classical Hanbury Brown twist HVT interferometer the options are exhibits interference pattern, the V's measures cross correlation, and C's measures autocorrelation. Between electric field and cross correlation between photocurrent and these measure autocorrelation between photocurrent is measure correlation cross correlation between electric field. So as sir already discussed in the class, this HVT is somewhat one detector in this way and one detector in this way. So whatever photon comes on this one, we use simply like photodetectors. So photodetectors generates the photocurrent. So whatever we measure, that is photocurrent, not the electric field. So these two answer is eliminated by this thing. And interference pattern also did not detect here, because we detect only number of photons whichever comes on this detector and the number of photons whichever in this on this one. Okay, so we know this. So from this what we know, measure the cross correlation or the autocorrelation, that is the question. Okay, so we measure the cross correlation. Okay, so this is the right answer here, because cross correlation means like we measure either coming on this one or coming in this one. So what for any detector, if the photon is detected in t plus tau, so that is somewhat this cross correlation, not the auto correlation. Okay, so next question is question 9. So question 9 is, for a given monochromatic light wave, with a constant intensity E0, the value of G20 is. So question is, for given monochromatic light wave with a constant intensity A0, comma, the value of G20 is. Options are A0 by 2, V A0 square, C is 1, D is 2A0, and E is 0. So the correct answer is 1. How? So how? The question is how. So just consider this amplitude is like something like that. So this is A0, okay? So this is constant. So G2, so I at time t will be A0 square, okay? So this is constant. So I at t plus tau is also will be A0 square, right? So sorry, this is intensity, okay? So this is not the A0 square, this is simply A0, okay? So this G2 at 0, if we'll see, so this will be at tau, this will be at time t, I at t plus tau equal to this I at time t square, right? So if we put tau equal to 0, then it will be I t ka whole square time average and I t time average of whole square. So this will be A0 square by A0 square, and it comes 1, okay? Remember? So next question number 10. So calculate the value of G20 for a monochromatic light wave with a square wave intensity modulation of plus minus 20%, okay? So your option is A 1.04, B 0.8, C is 1, t is 0.2 and E is 0. So what will be the question? Just solve in 5 minutes. So here the question is given. The question is given calculate the value of G20 for a monochromatic light wave with a square wave intensity modulation of I plus minus 20%. So here a point is given 1.04, which is the right answer, but how? So here I can explain it like the square wave is given like that, and the intensity is I0 if 1, then plus minus 20 means 1.2 I2, 0.81 0.8 I naught. So G20 value is given like average value of I at time t and I at time t plus tau, and divided by average value of time average value of I t into time average value of I t plus tau. So it is equal to it plus tau because it is constant like here. So this will be I t square y I t average square. So how can we calculate it? That will be I0, and t square is equal to I0. And what is the value of it square average? That is 1 by 2 0.8 I naught square plus 1.2 I0 square, and that will be 1 by 2 I naught 0, and it will be 2.08, right? Then we square this and then add, it will be 2.08, and then we can get 1.04 I naught square. So this g tau is equal to 1.04 I naught square divided by I naught square equal to 1.04. Okay, so the right answer will be 1.04. Okay, so in the same fashion, the next question is 11 is a source emits a train of single photon with exactly regular time interval between them. Figure 1 sketches the registered number of pulse using detector A, blue line, this is given by this line, and B, red respectively, this red one is. So let t be the time interval between the pulse and tdi be the detector response time. Okay, choose correct option in regards to relation between t and tau d, that each case. So first option is tda greater than t and tdv is less than t. So t is this much value. If tda will be greater than t, then how can we measure with detector d? So this will not be the correct answer. Similarly, tda is equal to t and tdv is equal to t, that is also incorrect. The right answer will be tau d comma a is less than t and tau dv is greater than t. Then only we can detect this type of signal. Okay, for the single detector. So the next question is the generalized coordinate qt plus and pt are equivalent to the and of classical harmonic oscillator respectively. So the first option is position and momentum, and second is momentum and position, third one is intensity electric field, and D is energy time, E is time energy. So the correct answer will be momentum. The Q will be the momentum, and Q dot is equal to like momentum. So the correct answer is position. QT is defined the position, and PT define the momentum in the generalized coordinate. So this will be the correct answer. Similarly, the next question is given the x1 and x2 quadrature of the field correspond to the end of the time dependent electric field respectively. So we know that the electric field will be like E0 sine omega t minus phi, right? So x1 and x2, so x1 x2 is this t, and this will be e to the power I kx minus omega t. So this x and t is in terms of sine and cosine. Okay, so x1 x2, so the correct answer will be here is amplitude and the sine and cosine of the time dependent electric field. Okay, so these are 13 questions. So the next question is to phasor diagram A and V of squeezed light or squeezed state are shown in figure 1. So figure 1 is given this is x1 quadrature and this is x2 quadrature. Okay, so phasor is given like okay, something like that. So the electric field of this one is given this is T. Okay, and second average of ET is given like that. Okay, similarly another one is given x1 and x2 is like that. So ET is given in same way and ET average is given like that. So the question is match the phasor diagram A with its corresponding field profile and identify the type of squeezed state. Okay, the options are A 2/4 to amplitude squeezed, B is A 2/4 to phase squeezed, C is A 2/2 to phase squeezed, D is A 2/1 to phase squeezed, and E is given A to third and phase squeezed. And F is given A to third to amplitude squeezed. Okay, so what will be the correct one? So in this one, if you say, okay, I will show you the question. So this is the figure you have to tell. So this is A to fourth, second or first. Which one will in your case? So this A1 will be the phase squeezed. Okay, the correct answer is A21 to phase squeezed. This will be your correct answer. Similarly, the next question is match the phasor diagram B with its corresponding profile field profile and identify the type of squeezed state. The options are is V24, that is amplitude squeezing, V is V24 phase squeezed, and C is V2 second, and this belongs to phase squeezed, and option D is V to 1 to amplitude squeezed, and E is V to third and amplitude squeezed, F is B to 1 to phase squeezed. So what will be the answer? The figure is same. If you see, so in this one, elongated along to x2, and here the squeezed in type of squeezed is amplitude squeezed. Okay, and the correct corresponding field profile is fourth one. Okay, so the answer is A is correct answer for this one. Okay, so the next question is number phase uncertainty relation tells that it is not possible it is not possible to know the photon number and the phase of the wave with perfect precision at the same time. Given below are two statements. In regards to number phase relation. The statement 1 is stated as the phase of a high intensity laser beam can be precisely measured, and S2 is given exact number photons in subpasonian night can be counted. So what is the options? Just A option is S1 is true and S2 is false. B option is S1 is false and S2 is also false. C is S1 is true and S2 is true, and D is S1 is false and S2 is true. So just read the statement again. The phase of high intensity laser beam can be precisely measured. That is true. And exact number of photon in sub-Pasonian light can be counted. That is also true. Okay, so both statements are true. So option C will be right answer. Correct. So these were the questions which are from the previous year assignment, which I prepared, and so one of the student also request that to elaborate on the fabrication process. So let's come on that one the in 15 minutes in this and the other and the sub latter video. I also elaborate the full process. So this fabrication process you can divide in 3 steps. One is deposition process, then second one is that is called lithography process or some patterning process, and the third one you can come to the removal state, or we can say etching process. Okay, so many process leads to the deposition, like many different type of deposition process are there. Some of like sputtering process. Number 2, it is given like CVD methods, that is called chemical vapor deposition, and PVDs are also there. Some spin coating, very common method. Okay, so like sputtering is something like you have some target and then you sputter it through the plasma of argon, and here is your substrate. Okay, so this metal is deposited on the surface and from this target, so this is called sputtering process. Okay, similarly the CVD process, we have one substrate is here, second substrate is here, we heat it and convert it in the vapor, and in the some tube we put the substrate here, and this process, this vapors comes here and chemically reactions inside, and then they deposit on this substrate. So this is the very rough process for the CVD, and there are many types of CVD process if you go into the details. And the PVD is also like, here we change the vapor from the physical meaning like heating or something like some electric sparking and all these things. And spin coating is like something we have substrate and then we put the drop, if you have some like PMMA or something, some organic molecules which can be dissolved in organic solvent, and you can put on the substrate and then it rotate by some speed and it will spread over the chuck. So this process is known as spin coating deposition process. Okay, so these are some common deposition process. Then we come on patterning process. So in patterning process there are many types of process which depends on your resolution, what resolution you need, how small you have to put. Okay, so in which you have photolithography. Okay, you have e-beam lithography, you have some direct laser, 3D laser lithography. Okay, and many more on this one. So if your feature size has till 2 micron or greater than 2 micron, then you can use this photolithography. Similarly, if you have less like nano structure around 100 nanometer or 200 nanometer, so you cannot go with photolithography, so you have to do this with e-beam lithography. Direct 3D laser lithography is also the same resolution with photolithography, but you need some advantage, like you do not need the physical mass. We will come on to that later. And one is FIV milling in this way. So in this one there is focused ion beam. Focused ion beam falls on your substrate and then it sputter your material. So you can sputter it in very designed pattern. So this is like milling. Your material will be etched when you do not need, and the pattern region will be remaining on your substrate. Okay, so this is type of milling process. Okay, so these are some very basic patterning process. We will go into the detail in later videos. And third one is etching processes. In etching process there are two types of etching process. One is dry etching and another one is wet etching. In wet etching we used chemicals to etch, like if you want to etch some metal. Okay, so we know that in the uh, some acids can etch the metals, right? So we use that one. Similarly, with some specific um, what it is called base and the acid combination can etch the uh, dielectric also. Okay, so this is only depend on chemicals. You have to more on chemistry side in this wet etching. And in dry etching, actually what we did, we flow the gas and that gas react with your material, and this material makes some another material which can be evaporated in the high vacuum chamber. Okay, so this is the process of dry etching. For example, like xenon fluoride, CH and CHCl3, oxygen plus oxygen plasma. Some material can be etched with only oxygen, in presence of oxygen, and CF4, CF3. All these materials gases are used to etching the material depending on the material. Okay, so we have to read some reaction of with the silicon or something with this one to choose the gas and all these things. Okay, so these are some basic processes which I explained here, and in later video we will go to the detailed patterning process, the whole process to pattern some small thing. Okay, so thank you.